Hello everyone. With this video, we are going to continue our problem of inferring functional dependencies. Right. So the input is we are given a set of functional dependencies, and then we want to know whether a functional dependency, y implies b holds or not. Right. So we are given x1 implies a1. Right. These are our input FDs, and then we want to know whether y implies b or not. As an example. Uh, right, if a implies b and b implies c, then we know that uh, a implies c, right? So this is the problem of inferring FDs, and we saw one technique in the previous video wherein we used something called as the Armstrong rules to to do our inference, right? And as I said in that video also, that using Armstrong rules is one way of checking for implied FDs, but there is another algorithm which is slightly bit more uh, easy in the sense that it's easy to remember and follow, because for the Armstrong rules you have to go really creative, what, whether to use argumentation and what to argument, and then sort of combine, right? It's good in theory, but in practice, not so nice. Okay, so for that, with that, let me get to this algorithm. This is called as, again, closure test only, but here we are doing the closure on attributes, right? So in order to disambiguate, I will the algorithm which I'm going to cover in this lecture is, I'm going to call it as attribute closure, whereas in the in the Koth slides which I showed, that is the functional dependency closure. Okay, so let's see how we do this. Okay, so let's say that we want, so we are given a set of functional dependencies, um, something like all of these, and we want to find whether y implies b or not, right? So we start with a basis called, as always, closure is written as, plus in the superscript. So I say that y plus is initialized to y, and then what I will do is that I will repeatedly look through my set of functional dependencies and catch any FD whose left side is a subset of the current y plus. If that is true, then I add a to the y plus, right? So this is how it goes. So let's say that you have a current value for y plus, which is this green set, right? So y plus is this, the attribute closure. So so y plus is also a set of attributes, right? And now you will keep on going in each iteration. You will scan through the set of all the functional dependencies which are given to you. Let's say x1a and x2 a2 and things like that, and then you will catch a functional dependency such that the left side, the complete left side of that functional dependency, happens to be a subset of your current value of y plus. If that is true, what are you going to do? You are going to absorb this right side of x implies a into this y plus, and that becomes your new y plus, right? So let us see a small example here. So let's say that this is your relation a b c d e, and you have these set of functional dependencies, d implies c, ac implies c, and so on, and I want to compute the closure of AC, right? And closure, as I said before, the closure is represented as AC plus. So we will initialize AC plus with AC, right? That's the base case, and then we will repeatedly go through these functional dependencies, the input functional dependencies, and see if there is any FD whose left side is completely coming into is completely a subset of your current uh, AC plus, right? So now we catch this functional dependency AC implies E. So here the left side is completely a subset of your current AC plus, right? So whenever that happens, you absorb E into your current closure value, right? So with this FD, your AC plus becomes ACE, right? So the E is absorbed. And then again, you again scan through your current, not current, the given set of FDs. And then you again try to catch an FD such that the left side is completely inside the current value of AC plus. So we have one such FD, I think it's AE implies B, because AE is now a subset of AC plus. So we catch something like this, you absorb B also, the right side of this FD also, into your current closure value. So AC plus becomes ACEB. Then again, you keep doing this until unless the AC plus stops changing, right? And at some point it will change, and certainly it will stop changing when this closure starts to contain all the attributes of this R. So that is the utmost dead end. But now if you have less number of FDs and all that, it can stop before also, right? So here I think ED is the last FD which gets expanded, and AC plus becomes ACEBD, right? So here I think all the attributes are now here in AC plus, so this set cannot go further anymore, so you just stop it. But in some cases, so for example, if ED was not there in your set of FDs, right, then would you have been able to expand this guy? I don't think so, at least not in this example. So then the process terminates, and then we say that now this is the key point you should know. So if the closure of AC, AC plus is ACEBD, if this is the output of the closure algorithm, then we say that AC implies whatever is the new set of attributes which got added. So the AC is always there, even if I write AC over here, that's really trivial, right? From your trivial functional dependency. Okay, so from the result of the closure, I get this functional dependency. AC implies EBD, and as you know, using the splitting rule, you can break it to get AC implies E, AC implies B, and AC implies D. Right. So now, if in your input problem, let's say you wanted to check whether Y implies B or not from the given set of FDs, then what you would have done is that you would have computed the closure of Y, and then you check whether you would compute the closure of Y using all these FDs, and then at the end of the algorithm, when the closure set does not change anymore, you check whether B is there in that set or not. If B is there, then that means Y implies B from these FDs. So this is the technique of using attribute closure algorithm to check whether a given FD holds or not. Okay, so remember this closure test, because we are going to use it in multiple ways. So we just saw one use wherein given a set of FDs, we could check whether a given test FD holds it or not. We just took an example, and then, right? So this is another way of checking for an FD, right? So Armstrong rules was the first one. This is the second one. This is more algorithmic in nature. You just follow the steps and you get it, right? Okay, now let us see yet another use of this attribute closure algorithm, right? Okay, so let's see how it is. So here the goal is that you are given a relational schema, let's say a relation R with A, B, C, D as the set of attributes, and let's say some FDs, A, B implies C, C implies D, and D implies A. And let's say that you decompose the relation ABCD into two parts, ABC and AD, right? We will be doing things like this during our normalization a whole lot. Now the question that I'm going to ask is, what FDs do hold on this ABC, right? Again, You are given the schema ABCD, and then you have these set of attributes, and you decompose the schema into two parts, ABC and AD. And then you ask the question that what functional dependencies hold on this smaller piece of the original schema. Right now, if you just check these FDs and see that, okay, AB implies C is the only FD which contains all the attributes of this broken piece, then you would be wrong, because these FDs can imply some other FD which will hold on this relation ABC, right? So for example, in this case, you have C implies A, which is also holding on this ABC. But C implies A was not there in the original list of FDs. You had to do some implication to check this, right? So now this is the problem. This is the problem of projection of FDs. You are given a relation schema A B C D E F, something like that. You are given a set of functional dependencies, and then you are required to project those functional dependencies onto a smaller schema, right? So here we wanted to project all these FDs onto ABC, whereas the original table contained ABCD, right? So we'll again be using our same closure algorithm which we covered here, right? So that's why I kept on saying that you make sure that the attribute closure algorithm, you understand it very thoroughly. It has two uses. One is to check whether a given FD holds or not, right? And how did we do that? We took the left side of the test FD, and then we computed the closure of the left side using these FDs, and then we checked whether the right side was there or not. It was one way. That was one use of the closure algorithm, attribute closure algorithm. The other use is to check for the other use of the closure attribute closure test is to project FDs, right? So you are given a relation schema, some set of FDs, and you want to project these FDs onto a smaller piece, right? So both these are very widely used. Let's now see how to project functional dependencies on the on a smaller set. Okay, now how do we do it? So basically, the key idea, I will of course cover a detailed algorithm. The key idea is to actually use the attribute closure algorithm that we studied. This is the attribute closure algorithm. We use this algorithm to study to get the closure of all the functional dependencies. So that means, using the attribute closure test, we are going to derive the set of all the possible FDs which can hold, and then from those set of FDs we are going to pick and choose which are relevant for our projected schema. And then depending on the algorithm requirements and all that, we may also do something called as getting the minimal basis. We'll cover more of this, but that's the overall idea here. Use the attribute closure algorithm to derive the set of all possible functional dependencies, and then sort of restrict or pick and choose which FDs are going to be valid for your projected schema, or that says which FDs involve the attributes which are there in your projected schema. So let's see the algorithm here, right? Okay, so what you do is that let's say, I think I should directly jump into the algorithm example itself, but let me just cover it quickly here. So let's say that your original schema contains your attributes A B C D E, let's say A B C D E F, and then some FDs are there on this schema, right? And now you want to project these FDs onto a smaller schema ABC, right? So then what you do is that you would take all subsets of this desired projection ABC. So all subsets of ABC is what? Null, and ABC, that is the trivial. and then you have the single attributes A, B, and C individually, then A, B, B, C, and AC, right? So you take all the subsets of this desired projection, and then for each of these subset, you compute the attribute closure using the original given set of FDs, and then you pick and choose which one are going to have all the attributes of the desired projection, right? Uh, Okay, so just a small thing that when you're doing these things, you don't need to compute the closure of an empty set or set of all attributes, because that is trivially set. Closure of an empty set will be empty, and closure of all the attributes, the entire projection ABC will obviously be ABC. So you won't be getting any interesting FDs from there, right? And then another thing is that if there is any subset of ABC, let's say A, and if when you compute the closure of A, if that contains all the attributes which you desire in your projection, then you don't need to compute the closure of any superset of that. Okay, so now let's go into an example here. So we have a relation R, A, B, C, D, E, and then we have some set of FDs which hold on R, and then we want to project these FDs onto a smaller relation containing attributes only A, C, and D. Okay, so as per the algorithm, what will I do? My first step is to list out all the subsets of ACD, right? So I think these will be the subsets of ACD. So single attributes, one, double attributes, and all the attributes, right? So here, as I said before, there are two subsets, which you can very clearly ignore. One is the null empty subset, that is not going to give you any FD, and this ACD, right? So your desired projection itself is ACD. So there is no point in computing ACD closure, because whatever FD that you get from ACD closure, that is not going to be of any use on this, right? So here I have shown this particular closure attribute closure value, but in reality it's not needed, right? Okay, so so I did this example. Let me know if there are any bugs here. So A plus will lead to only A, because I don't think there is any FD whose left side is only A. D plus will give you, first D is obviously there, and then from this you get DC, and then I think this also gets absorbed. So D plus is DCB, and similarly C plus is just CB, I believe, from this FD, and I don't think anything else gets added here. And similarly AC plus, we start with AC, and then from this FD you get E also, and then what else? Then from E to D you get D, and then C to B you get this, right? So AC plus is basically the entire relation R gets covered, right? So this is another thing which I wanted to show you. So AC plus, the result of AC plus was set of all attributes here, right? So whenever this is the case, you don't need to consider any superset of AC, right? You can just knock it out, because you won't get any interesting FDs. We'll cover more of this when we talk about minimal basis. But the key thing to remember is that while you are doing this, if for any particular set the closure, if that closure of that set contains all the attributes in your original relation, you need not consider any superset of this, right? So that is why even in your textbook also, the way you should the way you should compute these closures is that you should compute the closures in the increasing order of the size of the attribute set here, right? So first you do the singleton, then you do the double, and then finally the triple, as and when needed, right? Okay, so this is the so I have taken all the subsets here, and I have computed the attribute closure using my attribute closure algorithm, right? So from this output, I as I said before, I can derive the FDs, right? So A plus contained just A, so you don't get anything interesting. D plus contained DCB, right? So from here, what will you get? So from here, you will get DB as a new one. You also get D implies C, but that was already there, right? So there is nothing new that you're going to get. Nice. Oh, sorry. Okay. And C plus contained I think CB. Oh, this is right. Okay. So again from here you get C implies B, which is already there, right? And then AC plus contained ACEDB, right? So so when you're writing FDs from here, so AC you can ignore because it was there already here also. So you get AC implies E, AC implies D, and AC implies B, right? And similarly, you can write all of this, right? So this is what I was saying, that from AC plus you will get AC implies E. Now, if you compute the closure of its superset also, what you are going to get is that you will get the same set of things over here, but when it comes to getting a minimal basis, it will be of no value, right? Okay. And I can even quickly even tell you why that is the case here. So let's say you have this FD, right? If this FD is there, AC implies E, I can trivially get this FD. That there is no need to write this FD again, because so I can do full argumentation here. Let's say I put D on the left side and the right side, and then split the right side. So I'll get two FDs. ACD implies E and ACD implies D, which is a trivial FD because right side is a subset of the left side, right? So the moral of the story is that if you have any FD, X implies Y, you can sort of trivially attach something on the left side. You can say if X implies Y, then XZ implies Y. It is not of any much value. You'll see more of this when you go to 3NF and all that. That is why the reason is that when you're computing the attribute closure, if a smaller attribute closure of a smaller set contains all the attributes, then you simply ignore its superset. That is the reason. And because you are not going to get any interesting FDs from there. Okay. Nevertheless, let's focus. So we write all the FDs from all these closure values. So CD plus is going to give me this and all that, right? So after we do this, the next step to do is that from these set of FDs, the ones that you got here, you are going to select the FDs where both the left side and the right side contain attributes from only the desired projection, right? So just summarizing one more time, the way this projection of FD's algorithm is working is that it has two phases. So in the first phase, you are actually using the attribute closure to determine the set of all the possible FDs that may be relevant to this guy, and then from there you will finally pick, you will filter out which ones are actually the relevant ones, right? And for phase one, what you do, you compute the attribute closure of all the subsets of this desired projection, right? So let us see, right? So now which FDs from this set contains both the left and right of that FD should be from ACD, right? So let's see which ones are those. Okay, so from here you don't get anything. So D implies C but D implies C was already there. The same will continue to hold here also. And then from C you don't get anything because B is not of interest here. And then from this closure you get this, you'll get this AC implies D is what you will get. And then what else? So from ACD plus, as I said, ACD plus is the whole thing, so you won't get anything interesting from here. And then from CD plus, what are you getting? So you get CD implies B. Again, this is not relevant because B is not an attribute of interest to you. And then what do you have more? So I have from AD plus, I get AD implies C. This is also relevant for this particular projection. Okay. Then I just am showing here. Okay. Right. So these are the three FDs which hold on to ACD. Right. Now, if you want to determine a minimal basis, then this guy goes out. So basically what has happened is that so we are given three FDs now. AC implies D, AD implies C, and then D implies C. Okay. Then and now we are going to compute the minimal basis of this. Then this guy goes out, right? So a couple of things to remember here. So one is that minimal basis is not always needed. So even in the BCNF algorithm also, right, when you're doing the projection, you may or may not want to compute the minimal basis. Of course, the result will, your final result will vary a little, but nevertheless, the properties of BCNF will still hold. The only thing what may happen is that you may end up doing more work. That's all, right? So that is the reason why uh, if you open your textbook algorithm and you see the procedure for computing the BCNF, you will the textbook will say that you have to compute the minimal basis also after projection, right? But in my opinion, right, even if you don't do it, the only thing you will end up doing is more work. In 3NF, yes, minimal basis is extremely important. We will see that as we go forward. Another thing to remember is we sort of took this out because we had this FD which is already holding on ACD, right? Remember, all these three FDs were holding on ACD, and out of these three FDs I said that this was not needed, right? But if this FD was not there, then I cannot strike this out, right? So you should be very careful in the direction of implication. Given DC, you can say that this holds, but given this, you cannot say that this holds. The direction of implication is from here to here, right? Very similar here. In another, real world case also. So let's say that, again, that railway reservation system which I was talking about, given a train number and the date of journey, you can determine the number of sleeper coaches which it has. But if you just give me the date or if you just give me the train number, I cannot tell you the sleeper coaches, right? So you have to be very careful in the direction of implication. If you have this, then this is true. But if you have just this, then this is not true, right? So we'll see more of this in the minimal basis. Minimal basis is also known as canonical cover. That will be the next video.